All right, good evening, everyone. All right, we are recording now, and I just wanted to start off the class by pointing out to you that I have posted both with this week's lecture materials, and I've also posted an announcement after figuring out where to find it on the new Blackboard design to a fun survey. I guess you can be the judge of how much fun it is, but more fun than your average survey. All you have to do is guess my age. It's just a guess my age game. But the purpose of it is to get you thinking about confidence intervals, which I'll introduce in today's class. Maybe you'll understand a bit more about what confidence intervals are after today's class, and then you can go home, think about this survey, and answer it, and then I'm going to analyze your data and use it to discuss further in the next class. The basic idea of it is just both guessing my age and then putting some confidence intervals around my age to see what your understanding of confidence intervals is and whether it matches with my understanding of confidence intervals, which by the end of the semester it will. All right, so we have, in theory, two topics today, confidence intervals and the t-distribution. I'm going to try to take my time on confidence intervals, and we'll see if we get to the t-distribution. If we do, that's great. If we don't, that's great too. So don't hesitate to stop and ask questions during the confidence intervals. I feel like this is some challenging material now. This is maybe sort of here in the middle of the course. I'm kind of trying to pack some things in before you get to your final project, so that you'll have these things as you before I give that to you, and you have to get started on your own data analysis. But this is some of the most important and possibly the most challenging parts of the course. So I'm just going to take my time and take the time that we need. I'll start with a review of sampling distributions because it's intimately related to what we'll be talking now. And that will lead into a discussion of confidence intervals for the population mean and population proportions. You remember that mean is a measure of centrality for a normal distribution, or for any quantitative variable, but it's especially useful for normal distributions. And the proportion is for binary variables, things that only take two values. And then the last part of this is the t-distribution for confidence intervals from small samples. But as I said, I think maybe we'll just get to this a bit today because I don't want to overwhelm you. So who remembers how sampling distributions are different than population distributions? What's that? Yeah, a sample is just a part of the population. Very good. And what's a sampling distribution?
Average of samples.
You're getting close. So if you take a sample and you take the average, that is part of how you can get to a sampling distribution. And then, but that's just like one number, right? The average is just gives, if you take a sample and take the average, that'll give you one number. How would you get a sampling distribution? Yeah, very good. Yeah, you have to continue taking more samples. And so you take one sample, you take the average, that gives you one average. If you keep taking more and more samples and taking the average, you'll start getting a bunch of averages, and that's a distribution. That's your sampling distribution. And the sampling distribution is kind of hard to get used to, because in real life, you only ever see one point from the sampling distribution. Like, because you take a sample, you take the average, you just have one number. You don't get to see that whole distribution. You just get to see one point on it. But the concept's very important, because the way that we do hypothesis tests and get p-values and all of this stuff is based on some assumptions that lead us to what we think that sampling distribution might be. So the way hypothesis testing goes, and we're going to get more into that, as well as confidence intervals, is that we'll make some hypothesis about the sampling distribution. And that will give us in some cases, a normal distribution, in some cases, a t-distribution. It can be other distributions, but we make some assumptions under what is called a null hypothesis. We make this null hypothesis that says there's nothing interesting here, and if that's true, there's nothing interesting here, we'll know what the sampling distribution would look like. And then you have some practice now with, if you know what a distribution looks like it's a normal distribution where you know what the mean and the standard deviation is, you can look up on a table and calculate like the probabilities under the tails of that table. And the whole idea behind this hypothesis testing is going to be that if your one average from a sample is far out on the tails of that distribution, you're going to say it didn't come from this distribution. That's the whole idea behind hypothesis testing. And I'll be talking about that lots more this semester. But just to give you an idea of why I'm starting with sampling distributions and how that's going to lead into hypothesis testing and p-values. So population distributions are the distribution of some value among individuals in the population. So in an example of serum cholesterol levels, this would be everyone in the city, in the country, in the world, everyone's individual serum cholesterol level in those units. And that has some distribution. It's drawn here as a normal distribution with a fairly wide variance. So with the mean at 211, but varying all the way from 73 up to 349. So in general, individuals in the population can have quite a bit of variability in any individual measure. Like people are individuals, they can be quite different from each other. But one of the essential points about samples is that the average qualities or any average property of a group of a sample is going to be less variable than individuals. Right? Individuality is greater among individuals than among groups. It makes sense. And this shows up mathematically as a narrower probability distribution for the sampling distribution. So if the serum cholesterol level of individuals varies between 73 and 349, then the distribution of means among samples, this is samples of size 25, there's going to be less variability. So it only varies between, I don't know, 167 and 255. So remember that on this means if you draw a sample of 25 individuals from the population and take their mean cholesterol level, then the amount that you expect that mean of your sample to vary is quite a bit less than what you see among individuals. And that's not too surprising, right? And that is essentially the whole basis of inference, not just in this class, but going forward. That idea that that samples have a predictable distribution that you can calculate is the basis for all of the statistical tests that you will use in this class and in the future. And the bigger that sample is, the narrower that sampling distribution is. Like the means of mean cholesterol level of groups of 100 people are, hi Tony, are even less variable than of groups of 25 people. And that is why statistical tests get more and more powerful the larger the sample size is. The central limit theorem is this very useful way of calculating some things about the sampling distribution, even when you don't necessarily know all of the properties of the population. And it tells us that this sampling distribution for large samples has some very useful properties. And for any samples, this first aspect of the central limit theorem holds. So there were three parts to the central limit theorem. And the central limit theorem, just once again, it helps us relate the sampling distribution to the population distribution. The first aspect of the central limit theorem is that the mean of the population and the mean of the sampling distribution are identical. So if the population has a mean cholesterol level of 211, then the mean of samples taken from that population must also be 211. And it doesn't matter what size those samples are. And it doesn't matter what distribution the population is either. It just says that the mean of groups is the same as the mean of the individuals, as long as you take enough groups and average them. Now, the second part of the central limit theorem is maybe less intuitive, but no less important. That is that the standard deviation of the population is related to the standard deviation of the sampling distribution, or the distribution of sample means, by this formula, that the standard error is equal to, so this standard deviation of the sampling distribution has a special name. It's the standard error. So if you talk about the standard error, or you see the standard error written, you know that that is something special. That's telling you about the variability of a sampling distribution. And it's related to the standard deviation of the population by this formula, sigma over the square root of n, where n is the sample size. So the normal distribution is defined by only two parameters, right? What are they? Mean? Sorry? Very good. Standard deviation. Mean and standard deviation. And the first two parts of the central limit theorem tell you the mean and the standard deviation. So even though you never get to see this distribution directly, you know all about it. Oops, I didn't put number 3 on here. Why did I not put number 3? There's a third one. Who remembers what the third? There was a third rule in the central limit theorem that I seem to be missing here. Who remembers? I did it last class. I'll give a green star to whoever knows. What about sample? It does have to do with sample size. You're close. It's something to do with sample size. What about it?
The sample mean is the same.
That was the first one. Yeah.
Verbatim from the last PowerPoint, it's for large n, the shape of the sampling distribution of means becomes small.
Very good. Thank you. Let's see. Where is? I know that's not a great prize, but so yes, for large sample sizes, the sampling distribution is normal, and it doesn't matter what the population distribution is, the sampling distribution will be normal. So if you have random samples that are large enough, and for most purposes, just n greater than 30 is enough, that's amazing. That's not even that many people for a sample. But if you have a proper random sample of n greater than 30, you know all you need to know about your sampling distribution. You know that its mean is the same as the population mean, even if you don't know what the population mean is. You know that its standard deviation, or the standard error, is equal to the standard deviation of the population, standard deviation divided by the square root of n, and you know it's normal. All of that just from knowing your sample size, and the fact that your sample size is sufficiently large. What does none of these things about the sampling distribution depend on? Is there anything surprising that it doesn't depend on? There's maybe a couple surprising things that it doesn't depend on. Who wants to tell me something that's surprising in all of this?
The skewness?
The skewness? Yeah, so it is surprising that for a large sample size, it doesn't matter if your population distribution is skewed, as long as you have a large enough sample size. That's pretty surprising. Anything else? The second one I have in mind is really unintuitive for most people. It's maybe so unintuitive that you haven't even thought of it. The standard error of the sampling distribution and the mean of it and the normality of it, none of that depends on the size of the population. And that has some some pretty important and counterintuitive implications. It means that the sampling distribution that you draw your sample mean from, it doesn't matter whether your population is 100,000 people or 10,000 or 1,000,000 or 1,000,000,000. It doesn't matter. Yes? Okay, there's a good question. You're getting more difficult. What if we only have a population of 10 people? Then it does matter. If it's a small population, it starts to matter what the size is. As long as it's much bigger than your sample size, then it doesn't matter.
Is there a rule on that, how much bigger it does have to be?
Sorry?
How big common population has to be in order for this to work?
Let's say if your population is 100 times bigger than your sample, it definitely doesn't matter. If it's 10 times bigger, it probably still doesn't matter. If it's less than that, then maybe it's starting to matter. Yes?
So the population should always be bigger than the sample.
Population, well, what would it mean for a population to be smaller than the sample?
It means the sample is off.
Sample is off?
Like the sample reflects the population, right? Like a percent, like a small portion of the population.
Well, let's say we're talking about the population of students in this room. Can I take a sample of 100 students from this room?
No.
No, it's impossible.
Right.
Yeah. In the cases of small populations, things get a little more complicated, and you might have to go to things like simulation methods to do inference on a small population. You're not going to cover that in your program. But in practice, the populations of interest in public health are usually big. And the remarkable thing here is that it doesn't matter how big they are. So the thing that I think really throws people off is how can a sample size of n equals 30, a random sample, how can that be like a valid sample of 1,000 people or a valid sample of 100 million people, right? It kind of does, like, it's counterintuitive. And I guess the best way I can impart some intuition on that to you is that we're talking about like means here. All of this inference is about average properties. So, you know, we're talking about average serum cholesterol, average height, average properties of the group. And for those average properties, there's no need to sample some large portion of the group. Your average, any representative random sample is going to be enough to learn about the average properties of that group. If we were talking about extremes, like, you know, let's say we're talking about height. If you want to know about the average height in a population, just taking it like a random sample of 30 people and calculating the average is going to give you a pretty good idea of the average height in the population. Because even if there are some outliers, etc., it's not going to affect that average that much. Whereas if you're interested in the extremes, you wanted to know like what are the shortest and the tallest people, then 30 is not enough. So it's when it comes to like average properties of the population that a sample is a really useful thing to estimate those averages and to test some hypotheses about them. So the standard error tells us how much those average properties of a sample vary by chance, just due to sampling variation. And so the reason that it's okay to have a small sample from a big population is that the variability of that small sample only depends on the size of the sample, not on the size of the population. So if you have a small sample, say n equals 5, you'll see a fair bit of variability in those sample means. If you have n equals 2, it's quite big. It's almost as big as the individual variability. If you have n equals 30, then that average variability is less. And the important thing is that we know, if we know what the average variability of the population is, or if we know what the variability in the population is, then we know what the variability in the sample is. And vice versa. If we were to estimate the variability from the sample, we would know what the variability in the population would be, with some error. So as the sample size n increases, this denominator, sigma over square root of n, increases, and that standard error gets smaller. So the amount of variation you see in the mean of one sample to another gets smaller and smaller the bigger n is, and it does so in a completely predictable way with this formula. So the larger your sample, the closer your sample mean is going to be to the true population mean. This same rule applies with just a very little adjustment to sample proportions. So if instead of talking about like heights or cholesterol levels, I don't know, we were talking about right-handedness or something like this. If we were to take a sample of size 30 and calculate the proportion of right-handed people in that size, that's going to give us a proportion, say something like 90%. But if it's only a sample, we know that that's not a perfect calculation of the proportion of right-handed people in the population. There's going to be some sampling error because we estimated it from a small sample. And the standard deviation of that sampling distribution, which gives us an estimate of how variable those proportions are on a sample of our size, is given by this formula, the square root of the proportion times 1 minus the proportion over the sample size. So if we had, if we estimated 90% right-handed people from a sample of size 30, the standard error of that estimate would be 0.9 times 0.1 over 30, and the square root of that. So that would tell us we would have from our sample both our estimated proportion of righties and our variability in that estimate based on sampling variation. Any questions? So together, these things tell us everything about the sampling distribution. As long as you have a random sample, you know what the size of your sample is, n. And if you know what the population mean is and standard deviation is, then we will know what the sampling distribution of the means of the samples is. It will have the same mean as the population. It will have a standard error given by the population standard error divided by the square root of n, and it will be normal if we have a sufficiently large sample size. So let's see. Here's a question for you. Just a little test of your absorption. Let's suppose I'm going to consider this class, all of you in it, as a random sample of graduate students at CUNY. And of course, you know, there are some incorrect assumptions in there because you're not typical of graduate students at CUNY. I don't know, you're all much smarter and better looking. No, I'm just kidding. Let's say I don't know. I ask all of your ages in a survey, and from that survey, I have 36 ages, and I calculate the mean and the standard deviation of the ages of students from my class. Now remember, you're a sample of all of the graduate students at CUNY. But from your one sample, I calculate a mean and a standard deviation. That standard deviation, is that going to be close to the standard deviation of ages of all CUNY graduate students? Or is that going to be the standard deviation of a sampling distribution? So is that like an estimate of the population standard deviation or the sampling standard deviation? What's that? So put your hand up if you think that that is going to be close to the population standard distribution. You tentative hands. Put your hand up if you think that's going to be close to the standard deviation of the sampling means. Okay, so we have some of both. Well, tell me first, that standard deviation, is that representing the variability of individuals or the variability of the averages of groups of 36?
Individuals, because you only have one sample.
Very good. Yeah, that's the variability of individuals. We only have one sample, so that is not part of the sampling distribution. That's the variability of individual ages in this class. So it's going to be not exactly the same as the population variability of ages, but it's going to be a close approximation. And the sampling distribution, well, I could estimate that also, but I would have to take that standard deviation estimated from the class and divide it by the square root of n. And that would give me an estimate of the sampling variability in the means. So it's a bit of a trick question there. Remember it, that if you take a sample and you calculate a standard deviation, that standard deviation is an estimate of the population's standard deviation. It's not an estimate of a sampling distribution. That is an estimate, just like your mean, if the mean age in this class is an estimate of the mean age in the population, the standard deviation of ages in this class is an estimate of the population standard deviation. Yep.
Can you say that one more time, how to calculate this?
Okay, so if I take your ages, 36 of them, I can calculate an X bar. I can't see that. What's that? Use the green, okay. Where did I put the green? There we go. So X bar, that's the average of all of your ages. S, that's the standard deviation that I calculate from all of your ages. The standard error I would estimate as X bar over, or sorry, I made a mistake, over the square, Somebody tell me what it is. I'm messing it up. My numerator is wrong too. What's wrong with my numerator? This is directly on the slide.
It's the standard deviation.
It's the standard deviation. Standard deviation over square root of n. So here I don't have the population standard deviation like on there. So there, that would be an exact calculation of the standard error of the sampling distribution. In this case, it's an estimate. I don't have the exact standard population standard deviation. I just have an estimate from our sample. So this is going to be an estimate of the standard error. And sometimes you'll see like a hat or something put over that just to let you know that it's an estimate. It's not the exact value. So this S is an estimate of the population parameter of the standard deviation. N is known. There's no uncertainty in that. There is uncertainty in S. And this standard error, there will be some uncertainty in it because it's from an estimate of the standard deviation. But this S is an estimate of the population's standard deviation. Any questions? I'm happy to spend more time on it. It's important.
For the sample.
Sorry?
That will be the different sample and the population.
Yeah, this relates our estimate of the population standard deviation to our estimate of the standard deviation of the sampling distribution. And the sampling distribution are the means. So like if I went and calculated your mean age and then went and did the same for a bunch of other classes at CUNY, there would be some variability in those average ages given by this standard error. And of course that, I could imagine maybe in this class we have a range from like 25 to 40 or something like that. But the average is going to be a lot less variable than that. I bet if you went around and took the averages of all the different classes, ages at the School of Public Health here, it's only going to vary by, I don't know, from sampling error, probably only a year or something like that. If there's more variability than that, it's because of systematic differences between the classes. Like if we went to different departments or something like that, maybe there tend to be different ages of students, but that's not due to sampling error, that's due to something systematic. And the fact that you as a class are not actually representative of all graduate students of CUNY. You're only pursuing a couple different degree programs, and you have different career stages and histories than students in other programs. Any other questions? Okay, how about here's an easy one for you. If I told you what the standard error of a sampling distribution was, like if I said you took a large number of samples of size 30 and calculated that the standard deviation of the means from those samples was 10, how could you turn that into an estimate of the standard deviation for individuals in the population? What's that?
I said 10 times the square root of 30. Is that?
Yeah, exactly. Multiply it by the square root of the sample size, and then you would have your estimate of the standard deviation for the population. Okay. Let's talk now about estimation and confidence intervals. And this is the first bit of real inference that we're getting into in this class. What were the aspects of statistics that I talked about in the beginning? I think there was design, descriptive, and inference. So we'll do a little bit of design in this class, not too much, and we've done some descriptive statistics. That'll continue to be important, but the rest of what we're going to do is going to be pretty focused on inference and hypothesis testing and estimation, and all of these have to do with inferring something about the population from a sample. This is obviously something that is going to be useful if you want to learn something about a population given limited resources and being only able to perform a study using a few people from the population. When I say a point estimate of something, I'm referring to our best guess for the population parameter. So if I'm talking about, if you're giving, I'm going to ask you in this survey for your best guess of my age, I'm asking you for a point estimate, just a single best guess. And it doesn't tell you anything about how close your estimate is likely to be. So it doesn't tell you anything about the variability or the uncertainty in that estimate. Whereas an interval estimate is an interval between two numbers. So the other part of the survey that I gave you asks you to give an interval in which you believe my true age is. And I ask you for an interval within, it could be a parameter value, or in this case, my age, that you believe the true value falls, incorporating a so-called margin of error. that gives us some gauge of the accuracy in a point estimate. So this interval estimate provides an additional measure of the uncertainty in that guess, that point estimate. It says not only where you think the most likely answer is, but how how much uncertainty around that there is. And a population parameter and my age have something in common. What do you think that is? So it wouldn't seem like my age and, like, let's say the population average age in New York City. They're quite different, but there's one thing I can think of that they have in common. And that is that there's a single right answer. There's no uncertainty in what that, well, there might be uncertainty in what we know about that answer, but in the real world, there exists a right answer. So any interval that we put around it is only reflecting our uncertainty around what that right answer is. It's not reflecting like fuzziness in that, in what it is. Like, I know my age, certainly to the year. You gave me a little bit of time and a calculator, I could calculate it down to the hour. Like, there's an answer. And similarly, population of New York City, if we were able to, well, as soon as the census is done in 2020, there will be an answer. At a certain point in time, there will be a census that includes the ages of every single New Yorker. Short, just a little bit of movement coming in and out, but you could calculate the average age down to as many decimal places as you want because you have everyone's age. So if you take a sample and have uncertainty, you estimate that mean age and estimate a margin of error around it, that reflects our uncertainty in what the true answer is, but there is still a true answer that could be calculated exactly if you had all the information. So these interval estimates and margin of errors, they reflect our uncertainty about what a population value is, or in the case of the fund survey, what my age is. Okay, let's give a little bit more detailed example. Given a random sample of n equals 309 infants with a mean birth weight in that sample of 119.6 ounces, a standard deviation of 18.2 ounces, which is either A, known from the population, or B, estimated from the sample. So both of those are going to be something sort of close. One is exact, one is estimated from the sample. A, what is the average birth weight of infants in the population? And B, what is a 95% confidence interval on the average birth weight? So this first one, are we going to be able to answer that exactly? How come? No, we only have a sample. We don't have the whole population of birth weights. So we're only going to be able to give an estimate. What's our estimate going to be for the average birth weight of infants from this population? Anyone? Sorry?
Asking our estimate.
What is going to be our, let's say, our point estimate for the average birth weights of infants from this population from which this sample was drawn? Yeah, that was supposed to be a gimme question. Someone else answer me. I'll bet you didn't hear over here. Someone else answer me too now. Opposite end of the room. If you just had to give a guess, a single number that's going to be as close as possible to the average birth weight of infants in this population, what would your guess be? 119.6. Yes, very good. Given the information that we have, our best guess is going to be 119.6. We know it's not going to be exact because we only have 309 infants from the population, but that's our best guess. And that's because you remember the first, I mean, it's also kind of just intuitive, but going back to the central limit theorem, you remember that the mean of the sampling distribution is the same as the mean of the population distribution. So the sampling distribution moves around some. There's variability in the sample means that we get, that it's never going to be exactly equal to the population mean, but it's going to be centered on the population mean. So our best guess for the population mean birth weight is our sample mean birth weight. Now, what is the 95% confidence interval on the average birth weight? So this is our first question here that really gets at what is the use of all of this, of these sampling distributions. Because, you know, getting this point estimate was easy. It was just the same as, you know, well, if you can calculate the average from your sample, then you have your point estimate. But how, you know, how much uncertainty do you have in that estimate? Now, how close do you think this 119.6 is to the true average birth weight? The only way you can answer that is using the things you've just learned about the central limit theorem. Just as a note, this is not the same as what interval contains the birth weight of 95% of all infants. Do you know why that is?
And more
Yeah. Oh, in the back? Yeah, you said 2 standard deviations. Which standard deviations?
+2 minus 2.
Uh-huh. But how would you, what standard deviation is that? The standard deviation of like infant birth weights?
Yeah.
Yeah, right. So the mean plus or minus 2 standard deviation of infant birth weights would give you the interval in which 95% of infants will be born. But what I'm asking you is I've calculated the average birth weight from a sample, and I want to know in what interval should I be 95% confident that the population average birth weight falls. So I'm not asking about individual infants anymore. I'm asking about the population average. Well, we'll do it. You don't have to have the answer yet, but if you do, that's great.
Like that equation where we had like the mean plus the score and then that for this. It was like x bar plus the Z square. That's T.
Yeah, plus or minus standard deviation divided by, was it divided by something?
Square root of.
Square root of sample size. Yep, because remember our sampling distribution has a standard error that is equal to the population standard deviation divided by the square root of sample size. And that tells us that if we were to take repeated samples of n equals 309, it tells us how variable the means of those samples would be. It tells us that let's just say that this is known from the population, that individual infants have a standard deviation of birth weights of 18.2 ounces. The variability of average birth weights of samples of 309 is going to be 18.2 divided by the square root of 309. So those samples are going to have averages that vary quite a bit less than the birth weights of individual infants. And if you were to take that standard error and go plus or minus 2 of those, that's going to tell you in what range 95% of the sample means are going to fall. So we're going to put that to work. So starting from our sample of, say, 319 observations, we're going to calculate a point estimate that's just the mean of that sample, and a margin of error, which is the uncertainty above and below that point estimate, coming from the central limit theorem and how you've learned to calculate the standard error. So if you want a so-called 95% confidence interval, this is just how far above and below that sample mean that 95% of the probability for your sampling distribution lies. And you can do that just using the normal distribution, as long as either there's a big sample size, let's say more than 500, or the population standard deviation is known and not estimated as S. If you estimate S from some smaller sample, even n equals 50, you're going to use the t distribution instead. But don't worry about that too much yet. So here's some instructions for calculating confidence intervals from a sample. I'm going to give these first using the normal distribution. All you have to do is take your sample mean and add plus or minus 1.96 times your standard error to get the 95% confidence interval. So that's 95% of the probability for the sampling distribution. For a 99% confidence interval, it's 2.58 standard errors. And in general, for some other confidence interval, it's this plus or minus critical z-score for alpha over 2, where alpha is 1 minus that confidence interval. So if you wanted a 90% confidence interval, you would need the z-score for 0.05. If you wanted an 80% confidence interval, you would need the z-score for 0.1. And that's because you're going to construct a sampling distribution centered on the population mean and with a standard deviation of ST with 2 or 95, sorry, minus SE minus 2 SE. Whatever confidence interval we want, it's going to be the amount of a normal, the portion of a normal distribution containing that percentage of the probability. So if it's 95%, that's plus or minus 2 standard errors. If it's 99%, that's about plus or minus 2.58 standard errors. So this calculation is exactly like the probability calculations that you did for the normal distribution. It's just that you're using an X bar, a sample mean, and a sample or a standard error for that normal distribution. So you can do this both for a continuous variable with the standard error either calculated from the known population standard deviation or estimated from a very large sample size. Then you can go ahead and use your normal distribution. Or for a binary variable, such as right-handedness, where the expected number of right-handed and left-handed people are both greater than 5, or the number in the sample. So the NP is the sample size times the proportion. So this would be like the number of right-handed people, and this would be the number of left-handed people. As long as both of those are greater than 5, then this normal distribution to on a proportion is quite a good estimate. A bit about interpretation of confidence intervals. And these are important. These are common misconceptions about confidence intervals. These are pitfalls that I'll want to make sure that you're not falling into. So think about them carefully and make sure that you can convince yourself that these are not what confidence intervals are. So it does not imply that 95% of the population values lie within these limits. Right? That part I'm really trying to hammer home. Because remember, the confidence interval is an interval around the average, the population average. And that interval is generally going to be much smaller than the individual variability. So if we're talking about serum cholesterol, our uncertainty in the mean from a sample is going to be quite a bit less than the individual variability. So do not get confused about this and think that some 95% confidence interval represents individual variability. It represents uncertainty in the mean. Remember that the mean has some single correct value. If you knew everything about the population, the confidence interval represents our uncertainty in what that true value is because of sampling variation, because of sampling variability. It also does not account for bias in the point estimate. This is like I was saying that maybe if I were to calculate your mean age, divide that by the square root of and its standard deviation. Divide your standard deviation by the square root of 36. That's going to be divided by 6. So if you have, if there's a standard deviation of like 6 years, then, so let's see in this example, let's say the average age in here was 30. If the standard deviation was 6, that means that 95% of students here approximately would be between 30 minus 12, so between 18 years old and 42 years old. So that's probably even too large of a standard deviation. But the standard error there would only be 6 divided by the square root of 36, which is 1 year. So the standard error around the mean age that I calculated would only be plus or minus 1 year. And the 95% confidence interval would only be plus or minus 2 years, or 1.96 years. So that uncertainty in the mean is quite a bit less than individual age variability. But that estimate is only valid if you're a representative sample of the population that I'm interested in. So if I were to take you as a sample of all incoming CUNY SPH MPH students, then that's probably a pretty good assumption to make. But if I were also, I don't know, including PhD students, including some other school that has lots of people in their 40s coming in, it does not account for that kind of bias. It only accounts for sampling error, right? If you were to take another sample of size 36, it accounts for the amount of variability that occurs just due to sampling. So on the other hand, what it does do is provide an interval in which we are 95% confident that the true population mean lies. Does that make sense? And also, if we were to take a very large number of samples and calculate the confidence interval each time, those confidence intervals would contain the true population mean 19 out of 20 times. This is sort of a hypothetical example, but if you were to repeat your study a bunch of times, your interval would contain, if they're 95% confidence intervals, it would contain that true mean 19 out of 20 times. Or for another example, if you were to guess my age and give a 95% confidence interval and then go around and play like an age guessing game with a bunch of different people giving a 95% confidence interval each time, your interval should contain their correct age 19 out of 20 times. Not 20 out of 20, or else you're guessing too conservatively, and not 10 out of 20, or else you're being too overconfident in yourself. But if you have an accurate idea of what your uncertainty estimate is, then you're going to be right 19 out of 20 times. This population mean, like I have mentioned, is assumed to be fixed, to have some true correct value, but we just don't know it. It's not a random variable, and it does not have any error or variance. It's just some fixed value that we don't know. So there's no error, there's no variance on the population mean. This is similar to the one I already stated, but if we took repeated samples and constructed 95% confidence intervals around every one of those sample means, 95% of them would contain the true population mean as long as our sample is unbiased. And conversely, 5% of them would miss the true population mean. Just to look at that visually, this is actually a simulation that I did where I drew samples from a normal distribution and estimated a 95% confidence interval from each one of them. And I drew them from a normal distribution with this mean mu. And over a large number of times, I confirmed that 19 out of 20 of them cross the confidence intervals include this population mean. And you'll see that they shift left and right. That's because the sampling means vary along that sampling distribution. And you also see that some of those intervals are wide and some are small. That's because also the variability, like the standard deviation in the sample has variability. But if we have an unbiased random sample and 19 out of 20 of these confidence intervals that we estimate should cross the true mean. Boy, I'm really taking my time here. I'm going to finish up soon, and I think I will just probably, I'll just mention the T distribution today. But I have a Q&A for you. So is a 99% confidence interval larger or smaller than a 95% confidence interval? Ah! I heard larger, I heard smaller. Did I hear any other answers? Well, I'll put it this way. If I wanted to turn, let's say these are 95% confidence intervals, so 19 out of 20 of them cross the blue line. If I were to start them in the middle, but I wanted 99% of them to cross this line, would they have to be larger or smaller? Well, if I made them smaller, I took this one here and made it smaller, it no longer crosses the blue line.
Oh, it has to be large.
Yeah, they have to be larger. If I made all of these twice as large, I think all of them would cross that blue line. So to have more confidence that your interval includes the right answer, you have to make your interval bigger. Yeah, that's a very important point. The greater the confidence you want to have in your interval, the larger the interval must be. If you give a small interval, you're going to have less confidence that it contains the true value. Second, as the size of a confidence interval increases, does the confidence increase or decrease? This is basically the same question as the previous one. What's that? Yeah. Yeah, the bigger your confidence interval, the more confidence you have in it. If you say I am between 1 year and 99 years old, you can be basically 100% confident of that. If you have to give just a plus or minus 1 year, you're not going to be as confident in it. I'll see in your fun survey how well you've absorbed this. So as n increases, so the size of our sample, does the 95% confidence interval increase or decrease?
Increase.
So the sample size increases. Does the size of this confidence interval get bigger or smaller? decrease. Is that what you said? Think of it this way. If I'm estimating the portion of right-handed people in a population and I have to do it based on 3 people, I'm going to have to put a pretty large confidence interval, right? It could basically be between 0 and 100% for all I know. If I do it from a larger number, say based on 100 people, does that confidence interval get larger or smaller? Yeah.
Can you explain that again?
So let's say I'm estimating the proportion of righties in the population, but I'm doing it from a sample of 3 people, and I want to be 95% confident in that proportion. How big does my interval have to be? Just approximately. So I take 3 people and I see 2 of them are right-handed. My point estimate is 0.66. How big of an interval do I have to make to be, let's say, 95% confident that the true population value contains that interval? And I'm not talking about a calculation, just sort of an intuitive estimate. If you were going to bet $20 to say, for this particular population, the proportion of righties is between this percent and this percent, how big would you make that interval?
95%.
Big. Yeah, like between like 1% and 99%. Whereas if you took a sample of 100 people and you saw that like 65 of them were right-handed, you've got you're going to have more confidence in that proportion, right? Of 0.65. You can have a smaller interval around that and be 95% confident.
So the higher the population, the stronger the confidence interval?
Not the higher the population. Remember, it doesn't matter how big the population is. It matters how big your sample is.
Oh, okay.
So that's because that standard error is equal to standard deviation over square root of n. So generally, if you have 4 times as big a sample, your confidence interval will be half the size. And the larger n is, the smaller your confidence interval is. So the bigger your sample, the greater precision your estimates are. And what does the confidence interval tell us about the variability of individuals in the population? Not a lot. Very good. No, it's not about the individuals. It's about the uncertainty in the mean. That's a question that can trip a lot of students up. I mean, I could give you, in the example of birth weights, a confidence interval from a large sample that's very, very small, plus or minus 1 ounce, and then just ask you like what proportion of infants are born between 190 and 191 ounces, and it's not 95%. That's the confidence interval, not the number of, or the proportion of infants born with weights in that interval. So those are really broad misconceptions in the public and even among public health professionals that I hope you'll be able to go out and help other people understand too. Because confidence intervals are really broadly reported in the literature and even in the news, in polling results. Confidence intervals are really widespread. Yeah.
I'm going to ask a specific question about the survey. I've seen the American Community Survey, they have like 1 year estimates and 5 years estimates. And they always have this marginal.
They have what estimates?
1 year and 5 year.
1 year and 5 year estimates, okay.
I kind of wonder how they calculate that. How they can use that estimate. How they calculate the margin of error. It's accurate representation of the actual.
I'm not sure what you mean by 1 year and 5 year estimates.
Have you ever heard of the American Community Survey?
Yeah.
They have like 2 different sets of data.
Uh-huh.
One survey is
the
1 year estimates.
They do a bigger survey every 5 years, right? So those margins of errors are calculated essentially like this. It's a little bit more complicated because it's not a simple random sample. It's a stratified weighted sample, but the idea is the same as this. So if they're giving like a standard error on the like incidence rate of some outcome, or on like the proportion of the population of different countries of origin, or things like this, it is based on the fact that American Community Survey is a sample of the population that is done in between the census years. So, so they give you, and instead of giving you like individual data where there would be privacy issues, they give you these average values for areas, and they calculate those averages and a point estimate. They calculate a margin of error like this, and give you margin of errors. And then it's possible for you to then combine those. Say if you want to combine a number of the, I forget what the smallest geographical area of calculation is. Is it a census tract?
At least that is the one that is public.
Okay, so if you can combine the point estimates and standard errors for several census tracts to get a zip code or a state, but it is based on the uncertainty in what the true say population average is, because you're taking only a sample in these off census years. Okay, so let's go back to that example of 309 infants with a mean birth weight of 119.6 and a standard deviation of that sample of 18.2 ounces. So if I want to give a standard error on the population average birth weight of infants, I would calculate first the standard error by taking this sample standard deviation, 18.2, and dividing it by the square root of 309, and getting a standard error of 1.035. And because this is a pretty big sample, I'm going to go ahead and just use a normal distribution and look up in the Z table the Z-score for 0.025 or minus 0.025, and that's 1.96. You already knew that number. And then I can write out this confidence, this 95% confidence interval, and say we are 95% confident that the population mean is within our sample mean plus or minus 1.96 times the standard error, which is plus or minus 2.03 ounces. So I've just constructed a confidence interval that represents our region of confidence of 95% confidence in which the true average infant birth weight is, just from this one sample of size 309. And I didn't even tell you how big the population is. I'm just assuming it's big, and assuming that this is a random sample from that population of interest. And then I'm able to tell you that the true population average birth weight is 119.6 plus or minus 2.03 ounces. If I were to quadruple this sample size, so 4 times bigger to 1,236, then that halves the standard error and it halves the margin of error. So it's only 1.015. And if I wanted a 99% confidence interval instead, I would use this critical Z score of 2.58 instead. So this is for, let's see, this is for, so 2.58 times the standard error of 1.035. That's what the standard error was for the first question, n equals 309. And then we get a standard error of 2.67 ounces. So increasing the sample size made it smaller. Increasing our confidence level made it larger. Does that make sense? Oh yeah, I forgot, there's a few mini tutorials on our YouTube page. This is a link to one of them, but there are some other ones of them as well. And this one I calculated a 95% confidence interval by hand. Might be useful for you just to, I think it's only about a 5-minute video. I'm just going to introduce the student's t-distribution today to say that what we've been doing so far assumes either a very large sample size, like several hundred, or a known population standard deviation. But in many cases, our standard deviation will be estimated from a smaller sample. And in those cases, you will use the student's t-distribution instead of a z-distribution for calculating confidence intervals and later for doing hypothesis testing. And there's a pretty interesting story that I only know a little bit of for the student's t-distribution, but it was thought up, as far as we know, by this person, William Gossett, who worked for the Guinness Brewing Company and was doing quality control, and finding that, so he wanted to control, he would take like several measurements from a vat of beer and wanted to know, to estimate like what the, let's say, the alcohol content of that batch of beer was. And he knew about the central limit theorem and would use that to estimate like a confidence interval or do hypothesis testing, and found that the variability in the means he got from these small samples was actually too much. And he made this correction for small samples and proposed this new distribution, but because he worked for a company and it was a trade secret, he went and published it under a pseudonym Student. So he was just like Mr. Student. And I'll just say that these statistics are calculated analogously. Everything that you do in this case is going to be analogous, except that the actual table that you use, or the function in Excel that you use, or the procedure that you use in SPSS will be different. But conceptually, it's all the same. So all you really need to know is in which situations you use a normal distribution and when you use a t-distribution, and then have a little bit different procedure for carrying it out. And with that, I'm gonna shut up and say take a 10-minute break till 6:40, and then let Tony take over.